Hello! So this week we will do an experiment on simple harmonic motion. Basically, we will study simple harmonic motion on the example of the Hooke's law and on the example of the pendulum. So first, let's see what we have on the table. We have this Hooke's law apparatus here. We have a stopwatch. We have a mass hanger. We have one 50-gram mass, two 20-gram masses, one 10-gram, and one 5-gram mass. So this experiment is done from three parts. First, you're going to apply the mass on this spring here, produce the force, and then measure how much this spring stretches. Then you will plot a graph of the spring elongation versus mass, and then you will try to determine the value for the spring constant here. Second part is you will put masses here, move this into the oscillation, and then count how much time is required to complete a certain number of oscillations. From there, you will calculate the period for this spring, and then plotting the graph, you can find the spring constant for this spring. And then lastly, you will change the length of this string on which this mass is attached, and then calculate the period for this simple pendulum. And then by plotting the period for this pendulum versus the length of the string, you will be able to calculate gravitational acceleration. Okay, so let's start. First, your TA will tell you which masses you're going to use for the part 1 of this experiment, and you will record those masses in table on the page 28. Then you're going to first find the equilibrium position for this spring. The easiest thing to do this is move this ruler around here and then set a ruler so it measures either top or the bottom of this orange disc, and that's going to be your equilibrium position. So if you choose to follow the bottom of this orange disc, you have to be consistent when you do the measurements. Then you will start applying the set of masses that your TA told you. Let's say, for example, if I want to apply 55-gram mass here, it's going to be 5 grams for the mass hanger, and I will add 50 grams. So I'm going to suspend that. And then I will read the position, the equilibrium position for this string. You will repeat same measurement for all the values for the masses that your TA assigned to you, and then record the position of the equilibrium position. So starting equilibrium position, we set it to be equal to 0 because it's much easier to do all the other calculations from there. Okay, so now when you're done collecting the data for the first part, you're going to plot a graph of the equilibrium positions versus mass, and then use the equation number 4 to calculate the slope of that graph, and then to calculate the value for the spring constant for this spring. I will show you this graph business only once in this experiment, even though you're going to plot 3 graphs, but the basic idea behind this is the same. So on the y-axis, you're going to plot equilibrium positions. So you need to always label the axis. It's going to be here, y. You recorded the values in centimeters or millimeters. TA will probably tell you to record the value in millimeters. So this is going to be y. And then in units are going to be meters, and then you should write 10 to negative 3. Then on the x-axis, we are going to record mass. Your TA told you mass is in grams, so you can record mass in grams here. And you can say mass, and then units are going to be kilograms times 10 to negative 3. That way, the slope that you get will have a proper value. Okay, then you're going to put these 6 points on the graph. I'm going to cheat a little bit and then first get my best fitting line. The reason I'm doing this way is just to show you how to analyze the graph. So let's say I have my 6 points. So let's assume I first placed my experimental points, then I drew the best fitting line. So the best fitting line is going to be a line that's about the equal distance from these points. For me, because I'm cheating here, for me this best fitting, the line will go through the 0 here. For you, not necessarily this line is going to go through 0. It should, but because probably you're going to choose different scales for your y-axis and for your x-axis, your line may not go to 0. Okay, so the next step you need to do is you're going to choose 2 points on this line in order to determine the slope. So what I teach our students to do is to choose a point on the line between the first and second experimental point, and this point cannot be experimental point, and then choose second point on the line between the last and second last experimental point. Again, this point is not experimental point. So now you have your points A and point B, and then you're going to calculate the slope. So slope is going to be equal to delta y divided by delta m in this case. So that is going to be equal to by minus ay divided by bx minus ax, where b and a are the 2 points that you choose on your best fitting line. Once you calculate the value for the slope, it's going to be some value, and then units are going to be meters per kilogram, because you're plotting the equilibrium position in meters on the y-axis versus the mass that you applied in kilograms in the x-axis. Okay, so now when you have the slope for this graph, you need to use your equation 4 to calculate the value for the K, for the stiffness of this spring. So equation 4 states that y is equal to G over K times M plus Y0. You know that every straight line has a form of y is equal mx plus b, where this x here is actually the mass that you plotted, and then this m here in this equation is a slope, which represents g over k in equation number 4. So then you know that your value for the slope g over k is some number in meters per kilogram. You know the value for g, this is 9.80 meters per second squared. And then from here you can calculate to k, that's going to be equal to g divided by your value of the slope. And then units for k are newtons per meters, because k is the stiffness of this spring. It tells you how many newtons you have to apply to this spring in order to elongate it for 1 meter. Okay, so now we are moving to the second part of the experiment. You're going to move away this ruler here. Then you're going to apply the masses assigned by your TA, and then measure the time using the stopwatch or using your cell phone to see how much time is required to complete 25 complete oscillations. So complete oscillation, when you apply, for example, this mass of 55 grams, complete oscillation is if you disturb this here, this is 1, 2, 3. Little tips here, you can't do this because obviously it's not going to work. So you're just going to slowly disturb this from the equilibrium and then measure time for 25 oscillations. Once you're done taking data, you always need to take the mass off. Okay, so now you have the total time for 25 oscillations, and you know that period is the time required for one oscillation. Then you're going to calculate what's the period for this spring. Once you calculate the period for this spring, you're going to calculate period squared. Please note that here you're not going to use the equation for the period. Simply you're going to use a total time and divide that total time with number of oscillations in order to get the period for this spring. Once you're done that, you're going to plot equation number 5, find the slope, and find the value for K. So the goal of this experiment is to change the length of this string by winding it or unwinding it here. And then you will remove this mass from the equilibrium point by some small angle theta, and then measure the time required to complete 10 complete oscillations. Complete oscillation is this: 1, 2, and so on. So you will measure a time to complete 10 of these oscillations, record them to the table, and then you know that this time is required for 10 oscillations. Divide this time by 10 and get a period, which is time for one oscillation, and then square that number. Then you will plot the graph of period squared versus L, and then calculate the G for Houston. Okay, so that's it for this week's experiment. Thank you.